Okay, math, take two. You're like, take two? What happened to take one? Honestly, it ran too long and you deserve better. So I'm going to be more concise this time and we're going to try it again. Let's do some calculus. We are going to focus on single variable calculus today. We'll do multivariable later in the semester. So we're just going back to like AP Calc, 115, 116. We're going to look at derivatives and integrals in this video. The next video will have a little bit of other Calc 1 stuff. So derivatives are rates of change. That's the concept, period. We're done. Drop the mic, walk off. There are details to the calculations, but that really is the whole idea. We want to know how quickly or how slowly something is changing. Now, when you think about this graphically, this means that if you have a graph of a function, the rate of change is the slope. How steep is it or how shallow is it? How quickly or slowly is that quantity changing? So that's what we're doing. Now, I have this beautiful animation here stolen directly from the internet. And what's going on here is we have a function, that's the blue curve, and we're seeing the derivative of that function change at different points on it. So right now it's increasingly positive. It's very steep, very positive. Now it's leveling off. Now the function is flat, so the derivative is zero. Now the derivative is very negative because the function's decreasing quickly, and then it levels back off and blah, blah, blah. So on a graph, derivative is slope. Generally speaking, rate of change. Bam, that's it. So easy. For doing these calculations, well, hopefully you remember how to do slopes from algebra. Rise over run, baby. Y over x. Delta y over delta x. So that's what we're doing. Now, when you're working on a computer and you're doing finite math rather than continuous, infinitely exact calculations, you take your function, you break it up into a bunch of individual points, and you really do delta y divided by delta x. Calculate change in height, calculate change in x coordinate, divide. That's the numerical expression for the derivative. If we want to do things by hand exactly, so analytically, then you do take the limit as those delta x's become infinitely small. So as delta x goes to zero, the rise over run should converge to some particular value, which is the slope of that function at that exact point as you calculate that slope over a smaller and smaller and smaller interval near the point of interest. So, as I said, on computers, we can't do infinite numbers of infinitely small calculations. That's kind of bad. So instead, we do finite rise over run calculations over small values of delta x. You're like, what's small? Well, it depends. This is MSE. It depends. But what I will say is that usually in most cases, smaller delta x gives you more accurate results, closer to the exact continuum value, but it is going to be more computationally expensive. It's going to take more compute power to do a larger number of finely spaced calculations. Now, when delta x gets really tiny, things get wacky, but we're not going there. Okay, 3 rules for taking derivatives. These are the big ones. This is stuff that honestly I hope you remember from calculus, but if you don't, here we go. People forget, that's okay. We're going to review. When you have a linear combination of two functions, the derivative just distributes over them. So the coefficients, these constant terms a and b, those just remain constant coefficients. Nothing weird happens. They just sit there multiplying, and then you differentiate the function. When you have two functions added together, then the derivative of that sum is the sum of the individual derivatives. Most people don't struggle with that. If you have trouble, let me know. Now, product rule, this is a biggie for sure. And this has a little bit more subtlety to it because when we differentiate the product of two functions, we have to take two different derivatives. So what you'll do is you'll have the derivative of the first function times the second function. You'll also have the derivative of the second function times the first function. And then you add those two quantities together to get the total derivative of the product. Finally, actually, wait. At this point, people are like, I heard there's this thing called the quotient rule. What if you divide? Yes, there's a quotient rule. You can memorize it. I might remember it. I honestly might not. And you're like, that's weird. No, it's not because division is multiplication. Division is multiplication by the reciprocal. So if you have f of x over g of x, you can rewrite that as f of x times 1 over g of x. And then you can calculate your derivative using the product rule. Now, if you know the quotient rule and you like it, absolutely go ahead and use it. It's true. Great. Personally, not my thing, but that's what's nice about math. There's often more than one way. Okay. When we have a composition of functions, so now we have a function of a function, a whole function has been put as an argument into another one. This is where we have to do a little extra work because we have to figure out what is this outer function f and then what is the inner function g. Then we'll take the derivative of f of x, keeping g of x plugged in as the argument of that. Then we also need the derivative of g of x and to multiply those two expressions together. So df dx times dg dx. And that will give you the derivative of the composition f of g. This one is subtle enough that I think it's good to show an example. So here we go. We're going to have a function e to the negative x squared. Now, in this course, I am assuming that you remember your rules for derivatives of elementary functions, so that you remember that, how to take the derivative of a polynomial, derivative of sine, derivative of e to the x, log of x. If you've forgotten those, you need to put in a little time outside of class to relearn that and get it in memory. If you're confused, if you need help, come to office hours. I will absolutely help with it, but you are responsible for that prerequisite knowledge. So, assuming you have that, then you say, okay, I remember that the derivative of e to the x is, surprise, e to the x. Hooray! Well, that's easy. Looks like I picked a great example. But there's this stuff inside too. So we have our outer function, which is e to the something. We love that because derivative of e to the something is just e to the something. But this inner function is negative x squared. That's our g of x. So we also have to know the derivative of negative x squared. And when you write it out, here's what you get. You will get derivative of e to the negative x squared is derivative of the outside, which because it's e to the something, that derivative is just e to the something. So that's the e to the negative x squared on the left here. Let me do a little boop. There it is. So that is our df dx term. But then we also have that times the derivative of g of x. So then we need derivative of negative x squared, which is negative 2x. And then there it is. Derivative of g of x times derivative of f of x. So that's what we're looking at here. Okay, that's it for derivatives, at least for now. When we come back to multivariable, we'll have more to say. Now, for integrals, a lot of people have this idea that integrals and derivatives are opposites, and that's not wrong, but there actually is quite a bit more to it. So, what I want to encourage you to think of and to think about is something a little different here. Integrate, well, yeah. Let's first acknowledge the elephant in the room. Many people have feelings about integrals, yours truly absolutely included. I did not love Calc 2. I was like, why am I learning this? So if you love doing integrals, like, more power to you. I'm very happy for you. If you suffer through this, I understand your suffering, but we're going to get through it. Now, back to the concept at hand. There is an important distinction between indefinite integrals and definite integrals. When you are looking at an indefinite integral, this is the idea of an antiderivative. This is saying, okay, I want to find a function whose derivative is the function that I started with. It's a little bit like the logarithm logic that we did, where you're like, okay, I have to ask the question, what is the power of this thing that when I raise the base to a power, I get blah, blah. So it's a similar kind of thing, asking, what is the function that when I take the derivative of it, I get this known quantity. But the definite integral is not just the same thing as an antiderivative. And what I really want to push here, like I'm basically saying, hey, adopt this frame of mind. It's more productive and it's more accurate, honestly, is that definite integrals are about accumulation. They're about total amount of stuff. I know a lot of people have this idea in their head that like integral is area under the curve. That's not wrong, but it's a very limited view of what the integral is. That's only the case for certain specific ways of representing and doing and thinking about the math. The more general idea is that definite integrals tell you total amount of stuff. Now, I'm going to go off script here for a minute because I think it's worth talking about some physical examples. This is not just a like pure math being principled or pedantic thing. This really is very physically relevant and meaningful. So, for example, where are places that we use integrals in MSE and definite integrals to represent an accumulation of some quantity? One is so in kinetics, when we are looking at transport, we're looking at how substances move around. Maybe we have a solution and there are solute species of some kind, solute molecules in this solvent. And there is a membrane, and the solution is flowing through the membrane. And you want to ask the question, how much solute gets to the other side? That's an integral because your solute concentration is this continuous and changing dynamic function. So you can't just multiply because it's different values at different places and different times. You have to add up a whole bunch of tiny little changes to find the total amount. That's integration. That's accumulation. Another example, we'll look at batteries for a second. Batteries, you have charge carriers inside your battery, and they're getting pushed around by electric fields. But we don't really probe the electric field directly most of the time in batteries. What we care about is the energy per charge. What's the voltage of my battery? And in order to find that, you do an integral. You integrate the charge of your charge carrier times the electric field inside your conductor. You integrate that over the distance that the electric field pushes your charge carriers through. And so now you're adding up, you're accumulating all these little bits of work done on the charges in order to find the total energy that they get, which tells you the voltage. There's lots of other examples. I mean, heat transport, like stress and pressure and force. This is all over the place. But all that is to say that I really want you to broaden your idea of integral beyond just area under the curve, because there's more to it than that. Okay, getting off my soapbox. I already talked through this a little bit in words, but I want to show it symbolically as well. So we have a function little f of x. With respect to little f, there is some other function, big F, that when we take the derivative of big F, we get little f. That means that big F is the antiderivative of little f. And this is the connection between differentiation and integration, that the indefinite integral of little f, plus or minus any constant, is big F. Because then when you take the derivative of big F, you recover little f. So in this sense, derivatives and integrals do have this sort of inverse relationship. Now, as far as doing these integrations and finding antiderivatives and calculating accumulations, blah, blah, uh, I'm not obsessed with a bunch of clever tricks for doing integrals. I wasn't kidding. It was like my least favorite part of Calc 2. Uh, but my personal biases aside, most of most functions that are difficult to integrate are going to be integrated on a computer anyway. So while it is true that knowing some tricks for simplifying things by hand to make your computations faster and more accurate is a good thing, I don't want to overdo it. So I want to point out three particular methods of integration that I care enough about, and not just me caring, that's not great phrasing, but that are useful enough in actually doing work in MSE to be worth you investing some time in getting good at them. And they are U substitution integration by parts, integration by partial fractions. And of those three, if you have to pick one, oh, it's tough. I would give the edge to integration by parts. U substitutions are very valuable also, but integration by parts works really well with exponential functions because of the way that it works with derivatives um, being used in the integration by parts calculation. And differentiating exponentials is easy, which is why we love them. But if you do not remember these three things, if you don't know what I'm going on about, again, this is prereq stuff for the course. I am more than happy to help you with it, but you will need to catch up in that area. So if you need help with these three things, come to office hours, bring me your questions. I will work with you one on one and we'll get you caught up. So that's that. Now, for doing definite integrals, yes, when we have a single variable function and you have a graph of that function, you can calculate the definite integral of that function by plotting the graph and finding the area under it. That is true. When you are working with these things symbolically and not graphically, then we will use this antiderivative relationship to get the information that we need. And here it is on the screen. So when you're integrating from a to b, some function, you will evaluate that integral by computing the antiderivative at b, the antiderivative at a, and then subtracting. This is the fundamental theorem of calculus. If you don't remember why it's true, actually, I think I know of a YouTube video that explains it really well. So I'll try to remember to grab a link for that and share it on Canvas. Bug me in class if I forget, but I have a particular one in mind. Okay, that said, some some definite integrals you can do by hand, and it's occasionally helpful. Most definite integrals we're doing computationally. So when you do this stuff numerically, what you need to do is be really smart. Yeah, hopefully you can tell what my feelings are about integration. It is useful. That's why I have put in the effort to become good at it because it is important. All right. Um, so in the homework, in the exercises, yeah, I'll have a couple problems where I'm like, hey, write some code to do this integral for you using this method or that method, just so you get the practice. But my real advice for problems that actually matter, where the results are important outside of the purpose of you learning. Yes, you learning is very important. I hope that's well understood. I'm saying if the results affect other people, not just your learning, use professionally written integration code. It's going to be faster, it's going to be more accurate, it's better for everyone. Now, if you really get into this stuff, knowing which different integration algorithms are better in different situations is like the next level of understanding of this stuff. I'm not there yet myself. I'm not going to pretend to be. What I will say is that the three basic numerical integration recipes relating to this area under the curve idea are the rectangle rule, the trapezoid rule, and the parabola rule. What we're doing here is we're just using successively better and better approximations to a function in order to take that function, break it up into a bunch of small chunks, add together those small chunks to find the total. That's pretty much all I have to say about that. As far as why it matters, I don't know if you've noticed, but the universe is not static. We have not all achieved equilibrium despite the best intentions of the laws of thermodynamics. Which is good because if we were all in equilibrium, then nothing would ever happen ever, and that would be really lame and boring. So hooray for being able to calculate rates of change. That's all I have to say. I will see you in the next video where we'll look at Taylor series.